To continue with modern technology, we're now going to hear something about robots. Robots acting like humans. We are honored to have Professor Amitreza Kaseai here with us. Professor Kaseai is an associate professor of robotics and machine learning at the University of Groningen. His work spans robot learning, 3D perception and human-robot collaboration. His applications in manufacturing, agriculture and service robots. And last but not nothing, he has received several awards for his work, among them the Google Research Scholar Award and the Gratema Science Award. We are very interested in what you are going to tell us. The stage is yours, Professor.
So, good afternoon, everybody. Today I'm going to talk about teaching robots to learn like human, and how we can build the next generation of robots, or a collaborative robot, or cobot in general. But before diving into the topic, let's discuss about why is it important to do it so. As you probably know, a staff shortage affects our society in various sectors, including logistics, healthcare, agriculture, industry, and services. As a roboticist, I believe that personalized robotics can help us to mitigate this shortage effectively and efficiently. But what's the problem? Why we do not have such a robot yet? The problem is that these days, robot learning is like this one. So if a non-expert human user wants to do something with the robot, it should ask an expert user to come by, talk together, collect the data, and then train the robot. This process is complex, expensive, and time-consuming. Furthermore, it is not transparent, not personalized, and not scalable. Therefore, in our research, we try to make a breakthrough in robotics by enabling robots to learn rapidly new tasks over time, mainly based on interaction with non-expert human users. In particular, we add a non-expert user into the learning loop and allow it to do imitation and interaction and communicate with the robot. This process is affordable, easy, and fast, and make the robot learning scalable, adaptable, explainable, and also personalized. I'm going to show you how we can do that. Let's focus on imitation, how a robot can imitate a behavior that a non-expert human user can show to it. We develop a system that there is a camera mounted on the head of the user, and the user can record, for example, a server drink task, only one demonstration. And the robot will process this demonstration, detect the pose of the hand, and also generate, let's say, 1,000 instances of that demonstration in less than 1 minute, and use that data to learn a function that can replicate that task. Here you can see several examples of data augmentation that we have done. So from that single demonstration, we generate lots of data that can be used to train the robot immediately. And we test the performance of the robot, not only with the same object, but also whenever the objects are different in different locations. We call this a spatial arrangement. In the middle column, you can see that we tested with a different type of object, not exactly the same object that we use for training, and also with different level of clutter and background. And we observed that the robot was able actually to learn and to replicate that task easily without expert involvement. But the question here is that, is it enough to do like a demonstration? Is it possible to teach everything to the robot through demonstration? Our answer is no. The main reason is that some of those demonstrations are not executable by the robot. The main reason is that there are morphology gap between the body of the human user and also the body of the robot. Some tasks are not executable by the robot. Furthermore, if there is a small calibration error, it will lead to the failure. For example, stacking objects on top of each other. So most of the part of the task are correct and accurate, but only the last part, where the robot tries to put the object on top of the other one, there is a little bit of error. If we provide more and more demonstration, this problem will not be solved. How we can solve this one? If we develop a teleoperation system that can provide residual feedback for the robot only on the time that error happened, that would help the robot to correct this behavior. To address that problem, we developed this teleoperation system that there is a camera in front of the user, and the user can control the body of the robot and teach the robot how to, for example, stack objects on top of each other. Here you can see that the user has access to the right camera that is mounted on the left arm and right arm of the robot, and also what the robot can perceive through its head camera. And after those corrections, the robot is able finally to do that stacking object. It should be noted that all these tasks are like autonomous, and the robot, and there is no person involved. So the other point that we provide for a non-expert human user is interaction. This should be natural, physical, and also the safe. For example, if we ask the robot to put the leftmost milk box into the white bowl, the robot should be able to understand this one, decompose it to several primitive skills, and then sequentially execute those skills to accomplish the task. In the case of physical, we mean that the robot should also interact with the object. Usually in human-centered environment or future challenging environment, they are not isolated objects. They are a pile of objects and with different level of clutter. For example, in this clutter, if you ask the robot, get me the milk box, maybe at the beginning it's not possible, and the robot should manipulate the scene to make the target object graspable. Furthermore, there might be some uncertainty. A user actually may put something unintentionally to the trajectory of the robot, and the robot should be also aware of those type of collision and try to avoid those. I mainly focus on interaction for now. So grasping and manipulation, pick and place, are the main task that most of this cobot actually is doing in the industry. But let's think about future, if it becomes like challenging. For example, if you ask the robot to grasp the milk box, the highlighted one, initially it is not possible because of the surrounding object. So the robot should learn a synergy between pushing and grasping. First try to push the object to make it graspable, and then try to grasp it. In another case, most of this robot has a limited workspace. For example, if you ask the robot to put the Coke can into the gray basket, this is like challenging for the robot. But what happens if the robot learns a synergy between grasping and throwing, and throw the object into the basket instead of do pick and place, which is like a slow process? Here is the way that actually we process the scene. We use sensor data, mainly RGBD camera, to perceive the environment and detect which point is good to grasp. In this case, we formulate it as a supervised learning. I will not go into the detail of these techniques. We showed that the robot is able actually to clean the table even whenever we have like a pile of objects that randomly placed in front of the robot. In the case of large object manipulation that you do not see in most of the cobot system, current cobot system, is that two arms should collaborate together in order to be able to manipulate large, heavy objects. We formulate it as a reinforcement learning, and in the simulation we run 1,000 instances of the robot to learn this task. How should I manipulate large, primitive objects, as you see in front of the robot? And finally, we use that policy directly on the real robot. Let's back to this push and grasp scenario. Assume that we ask the robot to grasp the target object, which is the green toy object. Initially, it is not possible, and the robot should learn a policy to manipulate the scene in a way that the target object becomes graspable. Here you can see several real robot examples of that the robot is able to manipulate the scene to make it isolated and then try to grasp it. We tested out also in the using real world or household object, and we observed that the same policy can be used also for this type of object. let's check it out how the robot can throw the object into the basket. As I mentioned, pick and place is a slow process. And in most of the cases, maybe it's not possible because the placing area is outside maximum kinematic range of the robot. Furthermore, there might be some obstacle in the scene. So the robot either should do a handover task, first give the, for example, Coke can to the right arm, and then the right arm put it into the basket. This is a slow, very slow process. But the robot can also throw it into the basket. Because of the safety, we want to actually the robot, we teach the robot actually how to throw the object. So this is like initial kernel. And in the simulation, we try to optimize that kernel for different object, different basket, in obstacle-free, and also in multiple obstacle scenario. As you see that the robot actually is able to learn that policy. We observe that not only the robot is able to throw the object into the static basket, but is also able actually to throw the object into the moving basket. Whenever the human user actually move the basket and the robot threw it into the basket. You may ask how the robot actually realized where is the basket and what is the accuracy or what is the acceleration and velocity of the object. Here is an example of the perception part of our system, that the robot detects the pose of the object, the label of the object, and also the acceleration and velocity. And use all this information to calculate the parameter for throwing. So the next question is that can we combine all these primitive skills together? Because whenever the task is becomes complicated and long horizon, so it's hard to provide the demonstration. But if we teach the robot step by step and finally combine this primitive skill together, the robot is able to do all these tasks, more complicated tasks. So here we combine, for example, the isolation and grasping with the throwing. And the last topic that I'm going to talk about is the safety of the robot. That the robot should be able to adjust its behavior, especially in uncertain environment, not very well predefined environment. And you can see here in this example that the task is to place the object into the basket, and the robot and the user actually push an obstacle into the trajectory of the robot and also change the pose of the goal object. Similar thing that can happen, that in non-expert user can actually do some stupid action for the robot, but the robot should be aware of those situations and try to avoid obstacle and collision as much as possible. For learning, what is important is the data. And these days actually we have really good simulation. Currently, we are working on 3 levels: instance level, scene level, and task level, in order to generate enormous data for training robots that can act in various uncertain environments. Our work is central to many applications, or many future applications, ranging from logistic, assistive robot, agriculture, services, and also it can be used also in the healthcare to ease stress on patients and also for nurses. Thank you for your attention, and this was my presentation.